Okay, problem with sci-fi. So, at some point in your life, you have to come to terms with the fact that you'll never use the Force to pull a lightsaber out of a snowbank or to fly an X-Wing through space. Um, it's just what it is. The effects of gravity or lack thereof wreak havoc on the human body. The only thing that eventually, hopefully, we can achieve is the manipulation of gravity. And I have a nice video showing that, and I'll have to embed it in this topic so you can watch it at home. So this worksheet just kind of gets going on kind of addressing some of these kind of common science fiction things that we wonder about, and possibly science future things that we wonder about and have daydreamed about. And just kind of addresses them and see if we can kind of think of them mathematically. Now, this first one here, you're going to get going on in class on a remote day, but I just want to kind of read it, help you set it up, get you going on it, okay? So on a very large planet, close to a red dwarf star, there's not only gravity due to the planet, but also due to the star the planet is orbiting. All right, so that's on Earth as well, right? It's not just Earth's gravity acting on us. The sun's gravity matters, the moon's gravity matters, and believe it or not, Jupiter's gravity can matter as well. However, all of those gravities are negligible for the most part compared to the Earth's gravity on us, right? We see the moon's effect and the sun's effect on Earth in the effect on the tide, right? So the moon, just kind of a side illustration here. Here's the Earth. The water on the Earth's surface gets pulled. Now that's super exaggerated. It gets pulled towards the moon. And then it's because this side's farther away, it's not pulled as much. So you get this basically a bulge. The sea kind of bulges towards the moon as the moon orbits us. Now, the moon's rotation combined with the Earth's rotation causes the tides and the changing tides. The high and low tide aren't at the same time every day because not only is the Earth rotating, but the moon's going around us as well. If you ever live near the ocean, you'll experience that someday. You will pay attention to the tide. You cross over a bridge that has a big flat or something, and you see the tides out or in, and it shifts just like daylight shifts. But anyway, so that the moon clearly has an effect, and we have super tides when the moon and the sun are aligned, right? So that's something that can happen as well. Tropical Storm Sandy, or what did they call it? Was it Tropical Storm, Super Surge Storm Sandy, whatever that was, that flooded New York City a few years back. Part of the issue was it was a super high tide at that time when the storm surge came in. So the sea level was already a bit higher, but then a storm surge came and pushed and flooded a good portion of Manhattan with a foot of water or so, higher in some areas. But anyhow, this planet, the effect is going to be a little bit more multiplied, right? Because we see here at your location at a specific time, the gravitational field due to the star is perpendicular to the gravitational due to the planet. All right, so that must mean, I'm going to exaggerate it, right? I'm going to make myself a giant standing on top of this planet, right? So if the force of the star, so let's say the star somewhere over here, right? This is the red dwarf star. It's pulling on you, the force of the star, and we have the force of gravity pulling down. Now, the force of the star is 1/9 the force of gravity, but 1/9 is a pretty darn big percentage. So let's see here. Gravitational field strength due to the planet is, so G due to the planet is 13.2 newtons per kilogram. So a little bit stronger than Earth, right? 13.2 newtons per kilogram. Gravitational due to the star is 1/9 that. G of the star. Remember, G is the gravitational field strength at a particular location in space. So it could be anywhere. So it's 13.2 divided by 9, which is about 1.5. About 1.5 newtons per kilogram. So not insignificant. It might be a fun activity someday to figure out G due to the moon at Earth's surface and G due to the sun at Earth's surface. That'd be a fun activity to maybe think about. So anyway, perpendicular that way and this way, okay? So when you drop something on this planet, not only is it going to accelerate down, but it's actually going to accelerate towards the red dwarf star as well. All right, so that has an interesting thing. So let's say this planet orbits its star much like Earth orbits our star, and it rotates much like Earth orbits. Like literally, our day on this planet is the same as a day on Earth, where you get a full rotation. What effect would that have, right? You got to kind of step back. And the reason I made this problem quite a few years ago now was because in video games, right? I can think of various video games in my life that I've played where you'll be on a planet and the star or the sun of that planet is some massive red dwarf or something, or the moon is, right? The moon on the horizon, it takes up like the whole horizon. And well, what would that effect would that have? Well, it'd have a pretty significant effect. You can't ignore it, right? So anyway, just kind of an interesting little thing to think about. So we're going to work through this. You're going to try to do A, B, and C. It's multidimensional motion, right? Once you know this, it's basically AY is negative 13.2 meters per second squared, and AX now is positive 1.5 meters per second squared. So we have two components to acceleration. So it's projectile motion, but AX is not zero anymore, right? And the direction of AX is totally changing all the time. So you got to look at it at this problem at a snapshot in time when you're positioned so that the two are perpendicular, and go from there. All right? And the rest, calculate the speed. Remember, the speed of an object is always the square root of the x and y component squared, right? The magnitude of the velocity. All right. Well, I guess I did in part B for you already, so I'll leave part C to you. On the back side, you're going to talk about how high it was dropped from. Then we get into what happens as if the day on the Earth, it's the same, kind of what I talked about. Have you seen this in a video game before? Anyhow, we'll go from there. All right. This one's kind of an open-ended question. Also, just gets us thinking about how spaceships actually would have to move through space. Turns out the Millennium Falcon's physics are crazy, way off. Not to, for a variety of reasons, but, anyway. All right. Have a good one, guys. Just a little introduction to this worksheet.